Okay, thank you very much for the introduction. Hello, my name is Jimmy Juneau. I'm a graduate student at the University of Maryland with Bill Dorland in the Plasma Theory group. And it's my honor and pleasure to be here at AAS talking about my thesis research, which I've affectionately entitled A Deep Dive into the Distribution Function. Before I begin, I would be remiss not to acknowledge some collaborators, most especially the team for the code that I work on, which we call Jekyll. More on this in a moment. Now, this session is at least partially about computation. And one of the things that really motivated my thesis research was looking at problems in astrophysics that require kinetic theory from a new perspective. Now, what do I mean by that? Well, at least if you look at plasmas, the luminous universe, whether you're close to home in the heliosphere or further away in an accretion disk or the intercluster medium, all of these plasmas are weakly collision. Their mean free paths are much, much larger than other length scales in the system, things like the proton gyro radius. And the practical consequence of this parameter regime is that fluid models will break down. They will not completely describe the dynamics of the plasmas that you're interested in. And so you have to take a step back and look at what's called the Vlasov equation, or if you prefer, the Boltzmann equation, for the evolution of the particle distribution function in a six-dimensional phase space. That's three spatial and three velocity coordinates. Now, as a plasma physicist, this is the particular kinetic equation that I'm most familiar with. But this equation shows up everywhere in astrophysics. You could modify the phase space flux alpha, and then the left one would describe neutrino transport away from a supernova remnant, or you could modify the force to involve the gravitational potential, and then you're looking at self-gravitating dynamics, things like stellar dynamics or dark matter. And what remains to be done is an evolution equation for the forces. For a plasma, this is very naturally Maxwell's equations, and the system is coupled through velocity elements of the particle distribution function, things like charge density and current density. Now, this equation system is nonlinear. The electromagnetic fields themselves depend on the particle distribution function. And so we expect at some point we're going to have to rely on the computer to really model and understand these dynamics. Unfortunately, this equation system is notoriously difficult to numerically integrate because, as I said before, it's high dimensional, up to 6-dimensional plus time. Now, there are standard approaches to discretization of this equation system, Monte Carlo methods, where you would take the particle distribution function, you would discretize it as a collection of macro particles, advance those particles along characteristics given by alpha, and then sample the particles to construct the distribution function. Examples of this are the n-body algorithm, or in the plasma case, the particle and cell method. Now, there's a problem with this approach, and chief among them is the pollution of your solution with counting rules. This is a real travesty, because the particle distribution function is such a rich tapestry of the underlying physics of a collisionless or weakly collisional system. Just to take the plasma example, the wealth of data in the particle distribution function cannot be understated. You can take your particle distribution function and just by inspection understand energization processes that may be occurring, such as resonant interactions with waves if the particle distribution function is being deformed around the phase velocity of waves. Not to mention you can make spectacular movies of phase space, such as the evolution of the two-stream instabilities shown here, which is clearly showing trapped particle dynamics. We're further motivated to take a deep dive into the distribution function because of ever higher quality data being returned to us by observational missions. Close to home, we have the magnetospheric multiscale mission, shown here on the right, which is returning to us the electron distribution function as it crosses the bow shock and measures a magnetic reconnection. Or you can stay in the cosmological neighborhood, and we're getting particle distribution function data for stars in the Milky Way from Gaia data. Now, this is a hard numerical problem, and so we thought very carefully about the actual coding and development of a tool to actually analyze this problem. We do it with what's called the Jekyll simulation framework, which is a general purpose simulation framework being principally developed out of the Princeton Plasma Physics Lab. And yes, amongst the development team, there is a unstable, very not well-behaved branch of the code called Hyde that's not for public release, but the more well-behaved version of the code, Jekyll, is open source on GitHub. I don't have time to really tell you about the Herculean numerical effort that it was to develop this code. Instead, what I want to do with the rest of my talk is really motivate this approach of a continuum kinetic model. to really show you that all of the sweat and tears, if we're honest, a bit of blood that went into code development was worth it. So the problem that I want to talk to you about is competition between small-scale instabilities driven by counter-streaming beams of plasma. Examples of this are the electrostatic two-stream instability and the electromagnetic filamentation instability. Now, the astrophysical application of this work is there's still open questions about how the universe became magnetized. We theorize that it's most likely the turbulent dynamo that got us to the magnetic fields we observe today, but the turbulent dynamo requires a seed magnetic field, a magnetic field to start with. And the electromagnetic filamentation instability is considered a strong candidate for the growth of this, or the development of this seed magnetic field. Now, fundamentally, these counterstreaming instabilities are one-dimensional. You can show robustly in a one-dimensional simulation that the filamentation instability grows a magnetic field. But the universe is not one-dimensional. And in fact, as you move to higher dimensionality, even just two dimensions, things like the filamentation instability and two-stream instability will compete with each other. Not to mention the fact that you will have hybrid modes that develop. The classical two-stream instability is driven by perturbations parallel to the drifts, and the filamentation instability is driven by perturbations perpendicular to the drifts. But you can think about perturbations that lie in between parallel and perpendicular, mixtures of filamentation and two-stream, mixtures of electrostatic and electromagnetic modes. So what I'm showing here is a phase diagram of the angle of the fastest growing mode as a function of two parameters: the drift velocity over the speed of light, how non-relativistic the drifts are, and the ratio of the thermal velocity to the drift speed, how much of the beam's initial energy is internal versus kinetic. On the right-hand side of the phase diagram is a parameter regime that's been studied quite frequently in laser plasma applications. Here, as the drift velocities become close to the speed of light, the filamentation instability is easily the fastest growing mode in the system, quickly dominates the dynamics, and a magnetic field always robustly grows. But again, I'm thinking of an astrophysical application around the reionization epoch, where the drift velocities are likely smaller because the first stars and their supernovae were likely lower velocity due to the lower metallicity of the stars. And also the universe was likely colder. So let's look at this left side of the plot, where if your energy in the beam is comparable between the internal and kinetic components, say V thermal over the drift speed of a half, the two-stream instability is the fastest growing mode in the system. But as you make the beams colder, as you reduce this ratio, in fact, the linear picture even changes for what the fastest growing mode in the system is. And you start to see these mixture of two-stream and filamentation modes, what I call oblique modes, are as fast, if not faster, in their growth. So with this evolving linear picture, let's turn now to nonlinear simulations with the Jekyll framework. So the setup is an electron-proton plasma, with the electrons initially drifting in the y direction, and the protons initially stationary. Both species are also Maxwellian, and we start the simulation with random fluctuations in the magnetic field and the electric field. And we start them at very, very low amplitude compared to this initial energy in the plasma. So I'm going to show a movie here of what I call the hot case, this V thermal over the drift speed of a half, where we expect the two-stream instability to be the fastest growing mode. In the top right, you have the electric field and the magnetic field. And in the bottom right, you'll have two cuts of the distribution function, one in y versus vy, and one in vy versus vx. As you can see, the electrons here are drifting at some velocity, and they start initially Maxwellian. The two plots on the left are the evolution of the electric field energy and the evolution of the magnetic field energy. You'll see a red dot appear that's tracing the evolution of this movie in time. So very quickly, you see the growth of the two-stream instability. And you can tell it's the two-stream instability because it is quasi-one-dimensional. It's mostly in y with very little structure in x. But it turns out the filamentation instability is still present, just more slowly growing. And eventually comes to break up this structure, and a magnetic field starts to develop. But we're not done. The magnetic field is actually saturated. And we can ask, why is it saturated? As it turns out, if you look at the bottom right plot, the cut of the distribution function in Vy versus Vx, the distribution function is now elongated in y versus x. It's hotter in the Vy direction than the Vx direction. You have a temperature anisotropy in this system as a result of the two-stream modes decaying. This effective temperature anisotropy supports another instability, the Weibel instability. And that ultimately leads to a saturated magnetic field state. But what happens as you reduce this ratio, as you make the system colder? Well, again, we expect that oblique modes may grow faster. And as it turns out, that is the case. If we look at the electric and magnetic fields, almost immediately it's more structured throughout the domain. And while the magnetic field is growing, we're starting to see a magnetic field now collapse as the distribution function becomes more and more structured, as we send information to smaller and smaller velocity space scales. So the magnetic field is actually collapsing now here because these oblique modes are giving their energy back to the plasma isotropically. Unlike before in the hot case where you were left with an effective temperature anisotropy that ultimately supported the magnetic field, now we're left with a quasi-isotropic state and no magnetic field. To drive this point home, let's actually look at the evolution of this effective temperature anisotropy in time. The evolution of the temperature in the y direction versus the x direction. Now we're starting with drifting plasmas, so that is in essence an effective temperature anisotropy. And we see as the instabilities grow, this temperature anisotropy collapses. But in the hot case, it still collapses to a finite value. You can see that clearly in the end state of the distribution function, where it's elongated in y versus x. But in the cold case, it collapses to a value around 1. Ultimately, the distribution function is isotropic, and there is no means to support ultimately a magnetic field. We have no magnetic field growth from these instabilities. So we see a transition around a ratio of the thermal velocity to the drift speed of a fifth, where ultimately there is no magnetic field. And to really drive this point home, I've also plot in dashed lines one-dimensional simulations of the filamentation instability, where you see that no matter what this ratio is, a magnetic field always saturates. This physics here is the result of the higher dimensional simulations. It's a result of competition between these instabilities all growing at the same time, all competing with each other non-linearly. And I made the point before that I really wanted to motivate this continuum kinetic approach, this new way of actually numerically solving the kinetic equation. So I'd like to take this same problem and do it in with the particle and cell method, especially because these Monte Carlo methods are so common, and historically Monte Carlo methods have been used to study this same setup. What we find is that actually as you decrease the number of particles per cell, you get a quasi-saturated state in the magnetic field. Now, if you run with enough particles, you get a very similar result to the continuum kinetic equation, or solver in general, which is quite useful knowing that we're solving the same equation and getting the same answer with two different numerical methods. But if you run with very few particles, you get this kind of quasi-saturated state. So what's going on here? Well, let's first look at the particle and cell data for a really high particle run, or particle count run. Again, you see similar structure develop in phase space, and ultimately a low amplitude, unstructured magnetic field is left over. But as you run with very few particles per cell, you're left with short amplitude, or short wavelength, higher amplitude magnetic field structure. And what this actually is an analog of quasi-thermal noise, only it's in the magnetic field. Essentially, you have sampling error for running with very few particles, and that can give you the impression that you're left with a saturated magnetic field state, even though that's not the case. That brings me to my conclusions. So this is kind of an interesting problem to really map out the parameter space because it is relevant to these questions about how the universe became magnetized. We haven't really focused at all on the protons so far, but you can see a difference in whether or not you get a magnetic field depending on what parameter regime you're in. And really the point I wanted to drive home most strongly is that there are many problems, new and old, where a continuum kinetic approach can really be quite viable, whether it's plasma physics or potentially other fields of astrophysics. I didn't have much chance to talk about the numerics, though I published a paper last year on the numerics, and I'm happy to take questions about it. And I'm working on some follow-up papers that really show the comparison of the Monte Carlo method with our approach that I hope to publish before I defend my thesis in March. Thank you for your attention, and I'm happy to take questions now.
I have a question. In this
No, so all of the plasma stuff I was doing didn't have self-gravity. So you could think about adding terms to the kinetic equation that also include self-gravity and the gravitational interaction between the matter, but that is not done yet as far as code development.
So there is also no quake.
Right, there's no radiation in these simulations.
Okay.
Yeah.
So you made the comparison with particle and cell simulations, and you mentioned that the large number of particles per cell, you get similar results. So what's the difference in computation cost?
Right, so excellent point. The actual cost of the really high particle count runs is about the same as the continuum kinetic approach. In this case, these simulations were about 500 to 1,000 CPU hours. One of the things that I didn't really have time to talk about in this as well is I think another really strong motivation for this approach is also just, again, how clear having the particle distribution function makes the ultimate analysis of the simulation. You had the case in these examples where you could clearly see structure in the distribution function that was telling you about the physics that was going on. I really like to make the comparison here that, again, on average, a continuum kinetic approach may be more computationally expensive, but it's a little bit like flying first class or taking first class on a train. It tends to, on average, be more expensive, but sometimes it's a more comfortable ride. And what I mean by that is it can really reduce the number of human hours you spend doing analysis on your simulations when you have a noise-free representation of the distribution function, because it just contains such a wealth of data.
Another question? If not, let's thank our speaker again.